Hi, everybody. This is Joanne with Read Science, and after a few minutes of technical difficulties, we are here. And I'm here today, of course, with my co-host, Jeff Schomeyer, who's on his phone and has his own issues with that, but hopefully it will all go great. So we have today with us a pair of co-authors, and they're a great team because they've put a lot of books together. Let's start with their newest. Their first book is Magnitude, the Scale of the Universe, and this one is recent. Their previous one was a book called Light. I'm going to lose my headphones. Light, the Visible Spectrum and Beyond. And these are two great picture books. And then one that's a little more, well, it's got pictures, but more text-heavy is Your Ticket to the Universe, a guide to exploring the cosmos. I hear this is not how the cover should look. But we welcome today Kimberly Arcand and Megan Watzke. You guys say hi.
Hello.
Hi, everyone.
Okay. Yeah.
Starting, Megan Watzke likes to share, and I'm quoting from her, the wonders of science with the widest possible audience, which is what we really like to hear at Read Science. She has a bachelor's degree in astronomy and astrophysics from the University of Michigan, a master's degree in science journalism from Boston University. She's been a public affairs specialist for the Harvard-Smithsonian Center for Astrophysics, and also the press officer for NASA's Chandra X-ray Observatory. Here at Read Science, where science communication is our thing, we're always happy to talk with people who write, and I'm quoting again, Megan sees endless opportunities moving forward to improve the connection that people have with science. Welcome, Megan.
Thank you very much. Glad to be here.
Yes, Jeff, you always do the introductions so much nicer than I do. Sorry, Kim. Okay, so Kimberly Arcand is the visualization lead for NASA's Chandra X-ray Observatory, which has its headquarters in Smithsonian Astrophysical Observatory in Cambridge, Massachusetts. You're an award-winning producer and director, it says here, and a leading expert in studying the perception and comprehension of high-energy data visualization across the novice to expert spectrum. So what I'm very excited about is the fact that you were a molecular biologist before this, and you've been able to bring those skills to space study and exploration and explanation. Welcome. We're so glad you could come.
Thanks. Yeah, I'm really excited to be here.
And we let Jeff throw out the first question.
Oh, I get the first question. Okay.
Yeah, you always do.
That's true. I want to establish a sort of broad base from the first book, which I have back here, but you can't see it. So here I'm holding up Magnitude, which is a very lovely book, as we've seen from, have to remember, from this press. I don't have the right glasses on to read, but it's from Black Dog and Leventhal Publishers, who put out very nice books. And I want to clarify and then get an idea from you how you came about what the idea of magnitude is here. We're not talking about magnitude as just big things, as you might say, oh, such magnitude. But we're talking about magnitude as an idea that's very familiar to me as a physicist, that relates to things that can be measured, and then relating that to the universe. So tell us about magnitude, why you're doing it, and what magnitude really means.
I can go ahead and start, and Kim can jump in if she wants. So magnitude means a lot of things. Obviously in sort of everyday language, it means, heaviness or weight or importance. But obviously what we mean here is in sort of a scientific, mathematical sense. And that means being able to compare the size or the amount of something to something else. And the concept really came, partly from our day job where we are constantly talking about things that are really large, things that are really massive, things that are really hot. And we had to explain them in a way that is relatable. And often things in space are at some extreme end of a range. And so how do you really make that relevant for a non-expert? So, we are very much both big fans of the powers of 10. And that was one amazing way to sort of simply depict the range of physical size. Back in the day, I think Kim said yesterday, it's 40 years ago this year, that movie came out, or a version came out. Anyhow, excuse me. So what we wanted to do with this book was to show that there's this amazing range, not just on physical size, but on multiple physical phenomena, speed, pressure, rotation. There's, I can't remember the exact number, 13 or 14 different topics that we like to, share and explore that range of magnitude in each and every one of those. So it sort of starts with our day job and explaining the amazing things that space sort of, can, shows examples, but it really, there's so many examples throughout our daily lives too. That's also the impetus to come up with a book like this.
Yeah, exactly. So as Megan mentioned, we've been working for the Tanner Observatory for a long time. So Megan and I have been working together for a while. And that means we've fielded a lot of questions from the public at events and talks, through emails, through social media. And one of the biggest questions that's always on repeat is this idea of scale and magnitude. How big is this? How dense is this? How fast is it? Like, what are these sizes and how do we relate to them? And we've done a little bit of research on that as well through the Astronomy and Aesthetics project that kind of tries to figure out how both experts and non-experts look at different kinds of scientific objects, mostly astronomical, but also others, and then how they're able to comprehend different issues of scale and what questions they have. So this book felt kind of like a natural extension from those questions and those issues that we're constantly having to grapple with. Because you can talk about something being, 30 light years across, but what does that mean? And as she mentioned, a major reference point for us has been that Powers of 10 movie. And it was such a beautifully done video at the time, 40 years ago this year. Yeah. And to be able to take that and expand it into different subject matter. So it's not just the distance scale, but also, as Megan mentioned, whether it's pressure, density, area, and try to make that relatable to things we can, grasp a little bit more firmly down here on Earth.
In a previous life, I worked on a space shuttle experiment that did a physics experiment on orbit. And our particular experiment was critical phenomena, and we dealt with things like microkelvins and microgravity and all of these things. And so I see now, obviously, the connections. Like, you've been public affairs, science outreach people with Chandra, and the two questions I think that always came up when we were trying to talk to people and prepare statements about our experiment was, one, what's it good for? That takes a long time to figure out, but it's certainly worth knowing to tell taxpayers who are paying the bill. And the other one was, well, how big is that really? What can you relate that to? It's like, so suddenly I see, it's like, I can imagine exactly where that question came from. And so magnitude here struck me as two things, both of which are so far back that I don't remember having to learn them, but I think people find difficult to grapple with. And the one is the idea, it's like all these things that can be measured that you're talking about. You're talking about distance, you're talking about surface area, volume, acceleration, mass, and pretty much all the things that seem to be oddly central to physics. Like, this is all the stuff that I learned about it the very first time in physics. But then also this problem of orders of magnitude. An amazing thing that becomes an everyday shorthand in my scientific community. But what does orders of magnitude mean is a really exciting thing to get at. And then trying somehow to relate things that are a gazillion times bigger than these things that are a billion times smaller than that when it comes to looking at their distance from us, their weight, their mass, their length, and things. Okay, now I'm rambling. Joanne,
Well, I noticed something. I noticed that when you could, you sort of repeated a structure or a concept in each, each dimension or each concept, right? So if, red blood cells kept appearing through, so whether you talked about size or area or, velocity, or, all these things were repeated. And I certainly felt that was intentional.
Yeah, and actually, we weren't sure if that would seem odd at first, and we talked about it with our editor because we repeated supernova remnants a lot. So we both work pretty heavily with data on supernova remnants. Obviously, because of our day job, the Tanner Observatory takes unparalleled images of exploded stars and X-ray light, and I think our department does a really good job of helping to visualize those specific objects in these beautiful ways. But they can be still really difficult to talk about and to translate into scales that can be understood. So I think repeated Cassiopeia A as one specific example of a supernova remnant a couple times. And I think we had another supernova remnant in there as well that felt useful to us because you can talk about the area of a supernova remnant, and that's one thing, but you can also talk about the energy output, and that's something totally different. But when you can kind of get some of these pieces of the same type of object and then still keep relating them to other types of things, it's, I think, really helpful for that idea of relevance and being able to relate to them. With Cassiopeia A, I talk about it like nonstop, as Megan knows. She's probably sick of hearing me bring it up as an example, because like every talk I give, every possible thing I write about, it's always Cassie. It's this beautiful star that exploded many times the size of our sun. It's collapsed, ran out of energy, then exploded all over the place. So when we're looking at an object like that and we talk about how much area it might take up, now it's been expanding for 10,000 plus years. So it's, really quite big right now. And if you say, if you're looking at an image of Cassiopeia A and it's 30 light years across, all right, a light year is about 10 trillion kilometers. So you kind of can get a sense of that, but still, what does that mean? And then when you kind of extrapolate it down to the fact that the area of Cassiopeia A is about 40 million billion times the surface area of our star, and you can toss in the other 8 planets because they don't really matter at that scale, but that size difference is really interesting to be able to relate to. And the same thing when you talk about its energy output, or even our other book on light, I think we talked about the idea of atomic collisions in that one, and how you can relate that, something's going on in this beautiful pulsar and it's very far away, 25,000 light years or more, but something very similar happens in a neon sign that you see at the diner. So when you can get those kind of extrapolations and understand that there is a similar process going on here, it just gives you another, frame of reference for your own interaction with that information.
Yeah, I think just to build on what Kim said, I think if there is a common thread of all the things that we've done in our careers as have gone on, I think it's trying to make people understand or convince them that science isn't some other thing that happens with a small segment of people. Science is all around us, and it's something that everyone can appreciate and should hopefully feel not scared of or intimidated by, because I feel like what we're trying to do is to sort of make those connections between maybe something that seems like something totally foreign and esoteric, like whether it's a supernova remnant. We want to make sure people understand that those same physical processes affect them in their daily lives, and also that these concepts are things that they can understand. It's just you need to have it explained well to you. It's not that there are science people and non-science people. It's that there's sort of poor explanations and good explanations, good teachers, bad teachers, whatever. So that's one of the overarching big picture goals, I think, for our books, is to make those connections for people, so that people understand that science is all around us, and they can learn that the scientific process isn't something foreign or weird, or especially I think in this day and age we really need to work on making maybe not scientific literacy such a priority, maybe even just scientific receptivity. People are not so scared of science, and these books are one of our small steps to try to do that, I think, is because we feel like it's so important for people to feel comfortable with science.
So I want to just show this page. There's all the pages are great, but yeah.
I know that Labrador.
I know, this Labrador just caught my eye. So yay, props to your illustrator. But we start with the electron to DNA to a human eyelash. which, you know, not many people are thinking, oh, that has some mass, doesn't it? And yeah, to the dog, to the Hubble. And yeah, as we go on, we've got the blue whale, I think.
Yes.
Can't turn the page, but yes, the blue whale, Halley's Comet. You know, and I felt like, that's right. I don't sit around and say, oh, Halley's Comet has mass, but of course I know it does. I took physics, the Earth, and we've got a black hole and a galaxy cluster. And I felt it was really wonderful the way you go from very small to very big, or very slow to very fast. You know, everything goes, it scales up.
Yeah, and you know, you talked about, you mentioned the illustrations too, and that was another thing that we've never done before this book, is to, you know, have a whole book of illustrations. I'm a data person, so I'm usually like, images, data, you know, great. But with this topic, it really made sense to think about it differently. And I think the infographics provide a really nice continual visual that helps ground the whole book. In this idea of cohesiveness and relevance. The illustrator that our editor hooked us up with, Katie Peak, is an astrophysicist. So it was just like a perfect partnership to be able to get all of these topics illustrated so well to kind of help get those concepts across, you know?
Right, right. Yes, exactly. How do you do the mass density of the universe, you know?
Right. Exactly.
It's amazing.
The way especially when we get down to the really small sizes, you can't really image that stuff directly. Or when you talk about things like black holes, you can't image that directly. So there was a lot in this book that I think it made sense to take this different visualization approach through these infographics. And I just love the way they came out. Like, it feels very like it's telling a very visual story. And I definitely appreciated the way Katie was able to do that so beautifully.
Well, there, you know, as I was reading through the book after we received our copies, I was thinking, I want to give this to our school physics teacher. You know,
yeah.
I have a feeling he would love to have that in his library at school. And I have this feeling like at the holidays when this book is on the coffee table, people will be pouring through it because it's just, it's lovely, and it displays concepts. And my kids are very physics minded, so I think they're going to love it.
Great. We
I'm
hope
always
so.
happy to hear that. How foreign is the idea that physics works the same in distant galaxies as it does inside the human body? This is another thing that we, you know, from the beginning, and the excitement of Newton's universal law of gravitation was realizing that gravity is something that makes the apple fall on his head, but it's also the thing that keeps the moon in orbit. And it's easy for me to forget that that was a great new idea and a unifying element that physics and then chemistry and then we assume that they appear to work the same every place and at every scale. That really is a pretty remarkable thing.
Yeah, I think, you know, it depends on who you ask, right? If you talk to a scientist, they'll say, of course, right? That's sort of a given. Am I frozen, or is just Jeff frozen?
You're fine.
Oh, okay, sorry. I wasn't sure. It looked like there was a technical difficulty. So I feel like the concept of sort of this universality of science is not as well known as those of us who work in science think it is. I think people feel, you know, especially since there's so much pseudoscience out there, I think there's this sort of, unfortunately, a sort of, in certain segments of the population, there's a lack of understanding about how science works, and that the processes we're talking about for something that's either inside the body or on a microscopic scale or on a cosmic scale can have the same physics and underlying processes and rules and laws as do the things that you see walking down the street. And that's how our world works. I mean, we take, science is so embedded into our society and our lives. I mean, even just looking at your cell phone, I mean, how does that work? It works based on the understanding of, you know, lots of different science, including a little bit of relativity thrown in there with, you know, for GPS and all sorts of things. So I think that understanding that science is not some quote other entity, but it's just part of our our lives on a micro and on a daily and on a macro scale is not as well recognized as I think science people might think it is. So that's one of the reasons why we try to always tie the exotic or the unusual or the exciting science back down to sort of, relatable ways for everyday experience to show that they're not fundamentally different. They're just really cool examples of an extreme or something that maybe you don't see every day, but it's connected to your everyday experience, if that makes sense.
And I feel like that idea, like this holistic approach to science, I guess to use that term, is something that we've done for sure in our day job. We've been trying to do that as much as we can. The Tanner Observatory is, high energy astrophysics. It's looking at some really esoteric things, black holes, dark matter, not always so graspable. So I think it's been a challenge that we've had in our day job to be able to talk about some of these topics in a way that is more relatable. And we've tried to bring some of that to our books. I think the last 2 books in particular, we've done that the most because the topics kind of let us branch out, right? Exactly. Light, that Joanne's beautifully showing right now, and also magnitude too. Because you can talk about some of the most simple concepts and really learn a lot about them. Like, I was at a beach with my kids and niece a number of years ago, and I took this photo of their shadows on the beach. And I loved that photo because visually it was beautiful, right? But then I'm like, shadows, those are kind of interesting. And the more you think about them, the more interesting it becomes. All right, blocked light. All right, let's think about blocked light, And do we really use the idea of shadows in science? Oh, we sure do. I mean, you can look at astronomy alone, and the idea of blocked light has helped this huge explosion of discoveries around exoplanets, And so now we've learned about thousands of these exoplanets. And we find out things like, it's raining diamonds on one of them and it's raining sapphires and rubies on another. No big deal. So, I mean, the idea that just a simple concept of blocked light was the impetus that led to some of those other discoveries. I mean, they took spectroscopy and other stuff to figure out some of the details, but it was that basic underlying theme. So simple, the shadow. And what can that do for us in science? Well, it can do a lot. So yeah, that's something that I think we've been trying to bring out in our books just as a way to look at some of these really basic things that have a huge impact on what we know about the world around us.
So, and actually for those of you who don't have light, when did this come out? Was it just a few years ago, maybe 3 years ago?
2 years ago, 2015.
2 years, yeah.
Okay. So yeah, it just seems like I just got it, but I've had it. So those of you who aren't familiar with their book, it starts at one end of the wavelength spectrum and moves to the other end, much as this magnitude does. I thought that was a clever way to set this up. Is this the same illustrator, or it seems like you have a lot of images?
Those are all images.
Yeah. Those are almost all data-based images in that book, and that's my specialty. I do love data, as I mentioned. Right. So it was a pure pleasure to hunt down those images because there are just so many beautiful photographs, microscopic images, astronomical images.
And a lot of these are from NASA, so they're sort of public use.
Yeah, yes. Exactly. And we have fortunately grown a nice network of friends who are scientists, who are photographers, who we've been able to rely on for other projects. And they're all so gracious in letting us use their imagery in exchange for a couple copies of the book or whatever. So it was a really fun book to work on.
Because of course, any book like this, images are very pricey. So
yes, exactly. Yeah.
We all know this photo, hopefully.
Yeah.
Yeah, I mean, that book was really almost a direct extension of our day job, which is, if you work for Chandra, which is an X-ray telescope, the first question you have to ask or answer often is, what is an X-ray? Why do you, and also the second question is, why do you care about them? Why do you need another kind of telescope if you've got Hubble? There's a lot of these. And then that is a natural discussion of, well, there actually are many different kinds of light in addition to what we see with our eyes. And that simple concept alone is something that I don't think a lot of people outside of science understand, that there's different kinds of light. So really, it was just a sort of a labor of love, to be able to explore that and explain it and, find the coolest little facts about each kind of light and share that. And so that was a really fun project. And we have X-rays in there for Chandra, but it was the whole you know, as working in astronomy, so many times we have multi-wavelength images where we have different pieces of, the spectrum that we overlay together to tell the more complete picture. It's sort of like pieces of a puzzle. Even though people, and I don't think people fully, even though they love these images that they see, sometimes they don't know that they're seeing different kinds of light. And it sort of gets back to what Kim was talking about earlier. There's representation of data, different issues of color. How do you see something that's invisible? How do you make an image of something out of something that you cannot possibly see with the naked eye? So it's just a lot of stuff. It was fun to make. And, I think it's a fascinating topic. And again, one where there are examples in every wavelength that affect our daily lives that most people use daily, and they might not even realize it. So that was fun.
Right. This picture really caught my eye, because here's the things we use in our lives down below that fall on the different wavelengths. But then also these are some of the imaging satellites that are out there. Well, maybe not. That's not a satellite, but I thought, wow, that encapsulated it so nicely.
Yeah, and that's the sort of thing. I use that image or a version of that image to talk about this idea of the multi-wavelength universe a lot, because it's such a simple way to be able to connect these types of light with things that people already know and have experience with. If you're using a microwave to heat up that macaroni and cheese, if you're using your infrared on remote control, if you're getting x-rays at the dentist, I mean, just having a general familiarity with those different kinds of light. I think not everybody even realizes that they do. If you're a comic book fan, you think of the Hulk and how the Hulk got to be the Hulk. There are all these different kinds of light that are kind of there in our daily world already. So just putting a name to those things that you're already, familiar with, I think is quite useful.
Right.
It extends that universality theme that you see in magnitude of, yes, there are different kinds of light. Yes, these are all light. Yes, they are all electromagnetic waves. And so at some fundamental level, they're very similar, and you can understand them as different things, and you can understand them as the same thing.
Exactly.
It's really, really good. So these two books are very, Light and Magnitude are very visual books. And so was this, your Ticket to the Universe. So this was your first book?
Yes.
Sorry about the cover. It should be brighter.
Yeah. Yeah, so it's actually kind of, I don't know, Megan, I like this story. Maybe it's dorky, but so Megan and I never really had some grand plan to write books together. Like it wasn't something that we thought, oh, let's go write books, We write a lot of articles together for a day job, and I think we've both enjoyed writing creatively on the side in addition as well. And a literary agent, Elizabeth Evans, had actually seen an article we wrote together for, I think it was the International Year of Astronomy back in 2009. And she actually approached us and thought, have you guys considered writing a book? And I'm like, well, now that you mention it, I have, at least in my daydreams. So, I kind of like to give her a lot of credit for starting us on this really wacky path, because I don't know if I ever would have, thought to go out and get our own literary agent otherwise, but she saw something in what we had written together and put this little spark in us. And since then, we've just been unable to stop. And it's a little bit of an issue these days because we both need a vacation. But it's just such a pleasure. When you see, I'm a book lover, obviously, or else I wouldn't do this. But I have tons of books in my entire house. It's just stuffed with them. But so to go through all that work and to create this product that you can then hold in your hands, I know it's kind of old fashioned and traditional, but I just really love that whole thing from start to finish.
Yeah, I still love Your Ticket to the Universe for a lot of reasons. It was like our oldest child or something, It's, we didn't really know what we were doing exactly, but the premise of that book was fun, and I still think it's useful in that, again, going back to the same theme I keep going back to, which is, we wanted to make it accessible. We're both moms. We have a lot of friends who are moms who would have their kid come home from school and say, oh, I have to do my kid has to do a project on space, and I don't know where to start. And you would think in our day and age of the internet, you would have no problem. But I actually think it's almost worse because it's so overwhelming. You type in something about space and you're going to get 1,000 links and you don't know where to go. So what we did with that book was that we both like to travel, and so we tried to do it in a way that it's almost like a travel guide to the universe, which is why it's done the way it is, and the ticket theme and all that. Because I think the one thing that people were getting tripped up on, at least our friends who were parents, were, oh, I'm not a space person, so I can't possibly understand this. And the analogy we used there was, okay, you would probably travel to a foreign country even if you didn't speak the language, knowing that you had to learn some phrases or you had someone had to translate for you. You would still go and travel. It's foreign, but that doesn't mean it's unapproachable, or doesn't mean you wouldn't go. It's the same thing with space or any science. You just have to know the language. You have to have a translation. You need a guidebook. So we were trying to make it essentially a lonely planet for space without using that trademark expression. Yeah. Because we want people to feel, especially women and other people who are generally not feeling part of the science community, to feel comfortable with exploring space as if they would explore a country or a region which they had never been to before, in a similar way. So I think it's that was a lot of fun, and I think we tried to use analogies there too. We tried to make it the language in that as accessible as possible, as jargon free as possible. But it was, I'm sure we made some mistakes in there. So some were just being our first, and so but it's still a project I love to talk about.
So how you guys say you work together? So right now I'm gathering you're on different coasts. So how is this working?
Yeah, well, better than you might imagine. Actually, I feel like the bi-coastal nature of our relationship is actually a boon for us, because it's like, most of the time when we're writing these books, it's on the weekend or late on a Friday night or something. So, I can do something on East Coast time and then pass it over to Megan, and it's still a reasonable hour, and she can work on something and pass it to me, and I'll have it bright and early the next day. I mean, it's really actually helpful, especially with our schedules. We both have kids, and just, we're busy and doing stuff that needs to get done. So yeah, I feel like we've worked together remotely. Gosh, how many years, Megan? How many years have you been out in Seattle? I don't remember.
7 years in Seattle, but you were telecommuting, whatever, it gets complicated.
Yeah.
Your oldest is, I don't know, whatever.
Gosh, my oldest is going to be 14. So yeah, exactly. It's been a long time. So we've always had an easy rapport with each other, I think. And the time zone difference did not get in the way at all. I think we're both relatively good communicators on email and phone. So that probably helps. But yeah, it's always been a pretty seamless process for us. I don't know. I can't imagine having a better writing partner. So
yeah, we have this weird mind meld that we get each other very well.
It's weird.
And so I think, Kim and I, even though we're separated by distance, like there are certain things that just make sense to us, if that's the case, then we know we're on the right path. If it's too hard to explain it to one another or convince the other person, then we generally just drop it
out.
So I mean, I feel very lucky that we found each other work-wise, because I think it's been a really great collaboration for so many years, and hopefully many more.
Thanks.
Hopefully. So we need a vacation. We need a little vacation.
Yeah.
Well, you're currently in the promotion phase, so
yeah. After this.
Yeah.
Would you talk for just a little bit about what Powers of 10 is? I'm an older generation. It's very familiar to me and was very, it was just an amazing thing and influential at the time. And I love Ray and Charles Eames and this film that they made at a time when it was much harder to make films like that. But could you say what that is and how that's related to that, and to encourage people to watch it, because you can find it on YouTube now. And
sure.
It's really something that I think is still relevant.
I remember seeing it for the first time. I think I was probably in college. I'm not sure. And anyhow, it's a very simplistic film in its concept, and it basically starts out and on a blanket in a park in Chicago. I can't remember the name of the park. And it starts going out, with by orders of powers of 10, so 10, 100 times 1,000 times, and keeps stepping out until you get to the outer reaches of the universe as far as size, and then it zooms back in and goes into the body and goes into the person on the blanket, and then goes into the subatomic level, and so on, goes the other way. So everything is done by a power of 10, so that means multiplying or dividing by 10, which is that concept of magnitude that you were talking about, and understanding orders of magnitude, which are so important. It's such an important concept to understand, because I'll get back to that in a second, why it is, I think. But the Powers of 10 movie is just, it's a very short film. I can't remember how long, but it's not that long. But it very powerfully, pardon the pun, depicts the concept, and in a short period of time. It was brilliant. We love that movie and the books and all that went with it. And so what we wanted to do in Magnitude was to not just redo that, because it was so well done, but we wanted to expand on it. And so we wanted to take that concept of stepping through the powers of 10, or the range of things in these other concepts, whether it be mass or density or pressure. So the powers of 10 was definitely an inspiration, and we wouldn't want to fix what wasn't broken with that, but we really think it was just a brilliant thing to do. And just quickly about the orders of magnitude point that you had brought up earlier, Jeff, we find that there's just a lot of misconception, or maybe misunderstanding, about what even the difference between a million and a billion and a trillion is in these days. And people don't fully understand the difference. And, you can ignore, the extremes of science if you want, but you really should know what that means when it comes to, what's happening in politics, in our economy, in our climate, and all these things. So understanding magnitude and the orders of magnitude, it's not just sort of, I think, a luxury anymore. I really feel like in our society, you really should know that to be an informed citizen and make the best decisions for you and your family. So that's sort of my little soapbox about magnitude, and I will step off now.
Yeah, no, I mean, I think Megan raised all the important points, because, if you just look through your Twitter feed or toss on the nightly news or whatever, all those topics that they bring up, record number of stocks traded, 10 to the 11th, Google searches in the trillions, 10 to the 13th, distance to exoplanets, 10 to the 20th, stem cell research, 10 to the negative 5th, probably, whatever. All of these numbers, I mean, it doesn't matter what it is. It's millions of Spotify downloads. It's billions of tons of ice being lost in the Antarctic. It's trillions of dollars in U.S. debt. Exactly. Yeah. And those numbers, they grow and they grow and they grow. And it can seem so huge and so hard to grasp. I mean, you hear trillions, approximately what that means, but to actually quantify that, to actually be able to grasp that, to be able to understand the difference between a million and a billion and a trillion, it's not just adding a few zeros. I mean, it really, the amount of magnitude, the change in those steps is really hard, I think, to understand. So we try to do that through the book in a number of ways. We talk about time. I think time is one where I always like to start with, because I think it was Vera Rubin who did it first, when she, talked about how long it would take you to count to 100 seconds. How long would it take you to count to 1,000? Okay, we kind of get that. So how long does it take you to count to 1,000,000? How long does it take to, that would be what? Days? How about billions? Well, that would be years, and then if you want to count all the way to trillion, well, I don't know why anyone would, but that, quickly gets you into tens of thousands of years. So just understanding that difference, to days, to years, to that huge amount of time. I really think it's such an excellent illustration of the difference in those quantities and what it really means.
It's funny. Oh, go ahead, Jeff. Go ahead.
Two things. I had a professor once who always said he thought the perfect time for a science seminar was a microcentury, which is a useful thing to remember. But I think when Megan was talking, I was thinking it becomes something critical even for to be a good citizen when you hear things say this government program will only cost $100 billion, so we're okay, but we're going to have to cut this because it costs $10 million. And if people don't see that the relative magnitudes of those makes a huge factor in the propaganda effect, it's a big problem. They're being taken advantage of.
I'm just going to jump back quickly to excuse me, to the Eames. Charles and Ray Eames' grandson, he put together a short video about scale, and he says, I'm paraphrasing and I might muck this up a little bit, but he basically says that understanding scale is a form of literacy, and it's sort of, to not understand it is sort of it's a form of being illiterate in a way, because there's so many ways it affects you. And he thinks that understanding scale is kind of like the new geography. You have to be able to put things into context in order to understand what it means. So yes, is that program that they cut $10 billion from, is that a lot? Is that a little? Is that, again, that the economy and politics is just one realm, but there's so many ways. Is that hurricane that just, 10% more powerful and destructive? Is it 100 times? Is it 1,000 times? Like, understanding what the steps are and the real relationship is challenging, and I think really, really important given what's happening in our world today.
So the one tidbit say that the Hubble Space Telescope has the mass of 300 golden retrievers is amusing, illustrative and things, but and also I think subversive in a way, because it's easy for people to read, but it's also easy to remember. And those things, as they pile up in your mind, right, is what allows your brain, your mind, to make that induction of the idea of what magnitude is, so that you have all of these things piled up on it. It's not a simple idea. It's one that grows, and you come to it over time.
Yeah, and I think we tried to format the book, I think, a way to make that easier to process. It's not a book you have to read front cover to back cover, as Joanne is so beautifully illustrating right now. It's easy to dive in and out so that you can, go check out a section on time and understand it, and then kind of go back and check out acceleration, kind of a natural extension. There's, and I think it's a convenient book to be able to just look at a little bit, process it, go look at something else, process it, and it relates to so much. I mean, we've got the Winter Olympics coming up, for example, and there's going to be a lot of really interesting numbers thrown around just in the Olympics. And exactly, we actually use that a couple of times in the book. There are so many numbers being thrown around, and there's a lot of numbers in this book, and hopefully we did all the calculations right. So yes, numbers are really important, though. I mean, at the end of the day, that's, I think, one of the points that we're hoping people kind of take away, how important some of these quantities actually are.
Right, and I like what I was trying to sort of show is the compare, because when Jeff said 300 gold, we've got almost everything you've mentioned has a compare, and it will relate. The density of this is 1/4 of that, of the other thing on this page, and I thought that was very clever. And I could see a kid going, "Oh, that's cool. A typical ceiling fan rotates 40,000 times faster than the Earth rotates." Who knew, right?
I like the one idea. There's so many ideas, layers of ideas, which is good, because that rewards people for coming back, and there's more depth. But locating these images for comparison on the logarithmic scale, I thought was a very nice touch. It's one way to organize it. And the first time you read the book, it's cute, but you may not pay much attention to it. And then later on, it starts to add depth. And happily, with that depth, what you get, you start to get a better intuitive feel for what magnitude is. And you also, sort of through the back door, come to understanding what this really is for comparing these big and small things.
Yeah, you broke up a little, Jeff. Sorry.
Yeah.
Well, I was just the usual stuff. But the logarithmic scale is important, but you can come back to it later when you say, I wonder what that means. And when you look at it more closely, look, it repays that by giving you more depth of information and helping you understand magnitude and how to compare things, and how to understand it.
Yeah, I mean, just going back to that analogy of like a literacy with scale. I mean, I think you can have sort of that the analogy of a foreign language is that you're kind of getting some key phrases and some key basic understanding, and then over time you build fluency. You're not going to be fluent the first time around, but being fluent in scale I think I'm biased, but I think it's very important. And so hopefully this book can help you feel more comfortable with those initial useful phrases of scale, and then over time, if you can return to it and get more information, more detail, more breadth of your language of scale over time.
Megan, I love that analogy. You have to use that again. Yeah. Save that.
I'll forget it in 10 minutes. So.
Oh, no, don't do that. Don't do that.
It penetrates nicely that intimidation barrier of feeling like there's too much. I can never understand it all. I'll never be able to speak French. was, yes, learn how to ask where the toilet is, say what your favorite food is. After a while, you'll understand how to use logarithmic scales to compare things.
Yes,
Right.
exactly. I love that. Even the
And
toilet.
as Jeff always says, he says, everyone can learn science. You might not be able to do it in 5 minutes, but it can be done. And so I feel like this book is one way to do 5 minutes, 5 minutes, 5 minutes, and it adds up. And I'm going to say a curiosity that wasn't necessarily in the book, but it made me look it up. So you had the term undecillion, which is 1 followed by 36 zeros. Okay. And I went to look that up because I was like, why have I not heard, or why did that not stick in my brain when I saw it before? And they said, oh, in the US, it's a 1 followed by 36 zeros, but in the UK, it's 1 followed by 66. And I thought, who did that? There's no excuse for that. I can handle saying a lift versus an elevator, but don't mix up the numbers.
Yeah. Well, and the funny thing is, I think once you get past a trillion, it no longer has any value. And even trillion, it's still very hard for people to grasp. So we can put labels on these numbers as much as we want. But I think in the book, we tried to do this a lot, like going back to the example of Cassiopeia A, the area, we said it's like 40 million billion times, because it's already getting to the point where if you start tossing out trillions and even larger, those labels just don't add anything to the conversation, unfortunately.
Yeah, that's good. That's a good concept to get away from, to take away from the book. And especially if the names are going to be changing.
Yeah, exactly. If it's not standard.
And that's one of the reasons why when the names get sort of meaningless. And so at some point, when you're a little more fluent with scale, you need to be able to deal with scientific notation, which sounds horrible and scary, but it really isn't. So we do spend a little bit of time in the introduction trying to explain it, and there are other ways to explain it and whatever, but this was our attempt. And so, because at some point, if you really want to know the numbers, you have to be okay with understanding scientific notation. And it unfortunately, I think because it's math, or looks like math, people get immediately scared off. So one of the things is we want people to get away from that fear factor of, and again, that's further down the line for most people. If they're just dipping their toe into it, don't worry about it. But once you get a little more comfortable, that little exponent is going to be your best friend with really understanding what the real value is for that amount of whatever you're talking about.
And I mean, honestly, we kind of wrote a book that, this is something I could have used. Like, this is a reference that I really could have used when I was in high school, thinking about what I wanted to do with my life. And when I was in college and kind of being introduced to topics that I hadn't seen before, I really could have used a book like this to kind of help pave the way. Because I think we do a decent job of helping people understand that scientific notation and how it means something. Because I think in high school and even college, you just kind of get it kind of tossed in with everything else. But this kind of looks at it as its own importance. And yeah, I sometimes feel like you write the books that you want to read, and this is definitely the case in both this one and Light.
So for my battery died, Joanne.
No.
I wanted to read the dedication from Light, since we're talking about trying to make science, trying to invite people to enjoy science. But in Light at the beginning, you wrote, for those who love science and for those who don't love science. I was pleased by that.
Oh, yeah. It's right there.
Yeah, that's sort of our goal. Is I think we want to show everyone that anyone can be a, quote, science person. And maybe you've had a bad experience. Maybe you just assumed you were not part of the science, community or whatever. But we think everyone has the potential to be a science person. And trust me, we know that there's a lot of barriers for a lot of people, especially if you're of certain populations, that it is not a welcoming thing. So, we're 2 women, and we really feel strongly about having more women, more people of color, more people who are generally disenfranchised, to realize that they too belong with science, and it's not for some other, just white male dudes. No offense, Jeff.
Yeah, no, we had written, I think Megan had written this little tagline for our first book that you don't need a medical degree to know that you're sick. You don't need an advanced degree in literature to be able to appreciate a good book. And that's kind of the point here. You don't need to have a degree in astrophysics or physics or cellular biology or anything else to be able to have an access point to this type of material. And that's something we've been doing in our careers, for the past two decades. It's gone by fast.
Yeah.
But we start
wonders of science even more.
Yeah.
I do wonder. I know you want a break, but do you think there's another book inside?
Yeah, there is.
So we said we wouldn't be writing one for a while, but I don't know.
We just think it's such an exciting thing to try. I think we will definitely do something next. We don't know what that next quite is yet, but we will.
Yeah.
I think we're addicted, now at this point.
Yes, we are. We are.
They're amazing books. They're amazing books. I'm worried about you, Jeff. Are you going to disappear on us?
I may. The battery's saying, oh, you're only 12%, and look, my phone is heating up, and I'm fanning as fast as I can.
And believe it or not, I'm on my laptop, and I did not bring my charger, so I'm about to disappear. I know. We're all we need to understand how electricity works, so we know how to plug in our computer. So I'll be good for a couple more minutes, and then I think I'm going to organically fall off the wayside.
I think something's telling us something.
It's the end of the year pressure.
Right. So quickly, there's another book that you two were involved with that which I didn't have, and what was that book?
That was Coloring the Universe, and I can grab a copy off of my shelf and hold it up to the camera so everybody can see it in a second. But that's a book that we wrote with Travis Rector, who's at the University of Alaska. He's an astronomer up there who does some really amazing projects. He takes some beautiful images with a number of different kinds of optical telescopes primarily. But we all have a similar expertise level interest in working with the data to create these really beautiful images. And of course, these images are, beautiful, but they are images of science. So the idea was to kind of, in this book, step you through how most of these images are created, starting from like the ones and zeros, that binary code where it all begins, and then taking you through the steps of processing, smoothing, finding your field of view, some of these sort of aesthetic components of how to frame your image to, provide a more pleasing version of it, how to work with artifacts and removal if necessary, and then finally, how to color the data. And the idea of colorizing astronomical data is, for me, it's a really fascinating topic to talk about because I think a lot of people have this assumption that these are, giant space selfies, that, we take this snapshot and that's it. But most of these images have no color associated with them if we're going, non-geological type of images of, say, planets. So we have these black and white data sets that we have to work with, and how do you colorize them? How do you do that in a way that is both scientifically accurate, but also aesthetically pleasing? And then how do you talk about that? Because there is this issue that if you think it is the way this image is, if you could zoom in your spacecraft and get up close and personal to this nebula or this exploded star or whatever, there's this idea that you can actually lose trust from your viewer or reader if you don't properly explain how the images are created. And as I mentioned to Joanne earlier, it kind of starts even with other images that are much, much smaller. You have the same issues that go on with molecular images, and how you talk about that type of image processing and adding false color and all that. There's a lot of similar concepts that go on. So yeah, the book, I think, was a really fun exploration of that. It's a little bit more in depth, and I'll let Megan talk as I go get the visual to show, and I can be Vanna White.
Yeah. So, one of the most common questions that Travis gets, and we've gotten it over the years too, is, are these images real? And then they find out, and people want to know, how are they made? And then they hear that, oh, you use Photoshop. Does that mean you fake it? And, like they do with celebrities and so there's just a lot of misinformation, but we like to refer to some of these images, for lack of a better term, is space porn, because some people, just, love these images and they're obsessed with them. And then they find out, wait, but you used Photoshop, or you added color. Yeah. So they're not real. And then, so the whole point of the book was to explain that, yes, they're very much real. it's a translation from something that we cannot see with our eyes to something that we can. So it's very much trying to explain to people generally who already love space images how they're made, and sort of the, lifting the veil behind the Wizard of Oz kind of thing of how it works, to show that these are absolutely scientifically accurate images, and this is what's done to them. And in our professional lives, and Kim's more involved with this than I am, we try to be very upfront with what processing is and is not done, so that people can find out, and you can play with the data sets yourselves, even if you want, to show that these are not, colored by numbers. We're not making up data. We're not, painting in whatever we want. But it's a complicated subject. So it's, it definitely is for someone who loves photography, who loves astronomical imagery. But you have to already kind of want to be interested in, or already interested in this topic, I think. So it's a little more, it's not quite as a broad interest perhaps, but I think it's a really great book. I'm very proud of it too.
And the trust issue I can see is going to be an important time bomb to avoid in some cases.
Yep. Guys, I'm down to 1%, so I'm really going to die.
Yes, I was going to say, let's wrap it up. Is there anything you guys want to say before you disappear?
I guess just that the universe is yours to discover. So go out there and grab a book and have at it.
Just stay curious, and thank you so much for having us. We've had a great time.
Okay, thank you everybody for joining us and for bearing with our technical issues. And yes, I think we're signing off because we have to.
Exactly.
Thanks you guys for coming. You're wonderful, wonderful books so much.
Thank you. Bye-bye.
Thank you.
Bye, everyone.
Science. Bye.